Easy.
Does it record when you change screen?
Yeah, it does.
Okay, bet.
Yeah.
All right, cool. And is it recording webcam?
It's recording webcam as well, yeah.
Okay, bet. All right, so basically, welcome to the ENGG1300 crash course. We have our tutors here. Quang's going to go first, and then we have Farhan as well. So give him a round of applause. Introduce him and that. Yeah.
Okay, so let's get started. I'll give like a brief intro into the whole course first, and then we'll get started with statics, right? So ENGG1300 is broken up into two categories, statics and dynamics. Statics, we're pretty much looking at the whole base surrounded is sum of forces is equal to 0. Dynamics, sum of forces is not equal to 0. So you're pretty much moving in that case, right? Okay. So a few main topics that you guys are going to be looking at: forces, moments and structures, beams, SFD, BMD, AFD. So these each mean shear force diagram. This one is bending moment diagram. Oh shit. Bending moment diagram. And AFD is axial force diagram. Axial force. Are you gonna go through AFD?
No, AFDs. AFD comes like really rarely, so like doesn't come up in the course of anything, so don't worry about that.
Trusses, which is a pretty big topic. Frames and machines, and friction. What are you gonna be going through?
I'll be going through forces, just forces and moments. I think everyone should know forces and moments here, right? Like what they are, and I'm going through beams, SFD, BMD, and then truss analysis, and then yeah, that's what I'm going through for study.
Okay, so he's going to be covering these 4 topics, right?
Yeah.
Okay. Easy. Main topics for dynamics. So there's a brief introduction to dynamics, kinetics of particles. They're very similar, but not quite the same. But they are related to each other. Work and energy, impulse and momentum, and rigid bodies. So later on, when I go through the dynamics part of the course, I'll break it up into kinematics and kinetics. So down here. So I'll break it into kinematics and kinetics, and then we can break each one of these up into particle and rigid bodies. Okay? So I'll hand it over to Quang to start the static section.
Yeah.
Okay, so give us a sec. Okay, and then you finish. Okay, easy.
Right. Hello. How's everyone today? Good. So just starting. The first question is, who has done engineering studies in high school? So just majority of people. So yeah, this course's static part is pretty similar to engineering studies, like pretty much the same. So yeah. So we start off like, what is force and moment? So basically, force is just a vector quantity that causes an object to change velocity, direction, or shape. Forces has both magnitude and direction, and And what you gotta know is moment M equal F dot D. So for F is the applied force, and D is the perpendicular distance from the applied force. So so sign convention for moment is really important. So we're gonna know if it's positive or negative. So if a force is acting this way, right? Imagine this is a joint, and a force acting here is pushing down like this. So the beam is going into a clockwise direction, so that's is negative. If the force is acting up, that's going anti-clockwise direction, so the moment there is positive.
Do you want to draw it up, maybe? Maybe give him a better visual.
Yeah, sure, my iPad.
Yeah, sure. Yeah, we got markers.
Yeah. So just imagine if this is a beam, right? If there's a force, imagine this is a force pushing up into the beam. It's causing the beam to move in a anti-clockwise direction. Imagine this is a support here, right? that's allowed the beam to rotate, and that will move in a anti-clockwise direction. That force would cause a positive moment. On the contrast of that, if the force is acting downwards, that way, it's going to push the beam down into a clockwise direction, so that would be a negative moment. So yeah, that's pretty much all for sign convention. So now we move into beams. So this is the different type of load you could have on a beam. So point load, triangular distributed load, uniformly distributed load, and trapezoidal distributed load. So in this course, mainly we're going to cover the main three. Point load, triangular, and uniformly distributed load. So yeah. So now we move on to different type of supports. So we got three main one: roller support, pin support, and fixed support. So roller support has one reaction force, which is going up vertical. Pin support has two reaction, which is horizontal and vertical, and fixed has three. We got moment, horizontal and vertical as well. So yeah. Any questions so far? Alright. Let's move into one example then. So we got here a person standing on a.
What's the trapezoidal loaded beam?
Oh, it doesn't come up often, but the way you solve that is you split that into triangle. You can split that into triangle and wait, hold on, yeah. Let me make this look better. Okay, so you can split that into triangle and rectangular distributed load, and you solve that from there.
Oh.
So yeah, and the first example is a beam example. So we got a person standing on a diving board. The person weighs 54 kg, and the diving board weighs 36 kg. So you got here is where is it? Here's the weight force of the person. Here's the weight force of the diving board. So what's the joint here at A? Do you guys reckon? Is that a pin? Yeah.
Yeah, it's a
Pin. So yeah, so that's gonna have two reaction force there, and B is you see like a little roll, so it's gonna be a roller support there. So yeah, we got two support there, and always draw FBD diagram in these type of questions. It's gonna help you in the long run. So yeah, A we got two reaction force there, and B has one, and yeah, so the weight force of the diving board and weight force of the person there, WP. And yeah, so when we're drawing FBD, right, you can draw the direction in any way you want, up or down, but if you get the final answer as a negative, so you assume the direction originally wrong, so you got to redraw the direction of force. So yeah. So in any beam question, use three equations to solve. Sum of Fx equals 0, sum of Fy equals 0, and sum of moment at some point equals 0. Yeah, and then first, we solve sum of Fx equals 0. So you notice how we just got Ax here, but no other horizontal forces. So Ax equal to 0. Is that clear?
Yeah.
And then sum of Fy equals 0. So we got Ay plus By minus 353.2 from the weight force of the diving board minus 529.7 from the weight of the person, equal to 0, so we formed our first equation here. Ay plus By equal 882.9. And we can form the third equation from the moment, because Ay plus By, you got two unknowns and only one equation. You can't solve that equation, so you got to form the third one to solve the two unknowns. So moments, right? So here By is acting upwards from 1.2 meters from point A. So we're taking moments at point A. So if it's acting upwards like this, it would cause a anti-clockwise moment. So that would be positive. So it would be By times 1.2. And then we go to the weight of the diving board, which is acting down like this. So that would cause from joint A to have a clockwise moment. So that would be negative. So that hence the negative sign there. Hence the negative sign there times 1.4. And then same as the weight force of the person here. Weight force of the person there 529.7 times by 4.6, and then equal to 0. So then we got 1.2 by equals this value, and divide that out. By equals 2,737 Newton. And yeah, we solved by, and now find ay. We can just sub into the original one, and ay equals to negative 1,854 newtons. So notice how it's a negative answer, so we guessed the original direction wrong. So ay should be, the correct diagram for this, ay should be pointing downwards like that. So yeah, that's basically all the answer. So they asked us to draw a free body diagram, which we did, and determine the reaction at support A and B. So yeah, we answered that question. So that's all done. And now we move into UDL, uniformly distributed loading. So the main type in this course is going to be rectangular and triangular. So how I like to imagine UDL is like books on a shelf. So the force is spread out equally onto a beam. So how we solving this is just simplifying it to one single point load, like this. So everything combined to one force going acting down. Yeah. So for rectangular UDL, the force for any UDL, the force is just the area of the UDL itself. So for the rectangular here, we got a beam of 6 meter long with the UDL of 20 kilonewton per meter. So the force simplified down is 20 times 6 equals 120 kilonewtons, and for rectangular it acts directly in the center. So yeah, it acts 3 meters this way, 3 meters that way. And now to the triangular UDL. So the area of the triangle UDL is half times base time height, that's the area of the triangle, half times 6 times 20, which is 60 kilonewtons. So the point where the force acts is 1/3 from the big side of the circle. Yep. So yeah, this is the big side of the circle. If it's flipped over, so it's just always 1/3 from the big side. So 1/3 of 6 is 2 meters, so it's at 2 meters from this point. So 60 kilonewtons acting down there. Any question on UDL at all? No. Okay.
I got a question.
Yeah, come on. Yeah.
So like, you see the height. Can you explain where the height comes from?
The height come from? So the height is like the intensity of the UDL.
Is it the maximum intensity?
Yeah, maximum intensity UDL. Yeah.
And in this case, it would be 20, right?
Yeah, 20 kilonewtons for both stuff. Yeah. Yeah. Any more questions at all, or am I going too fast or too slow? Good. Alright, let's go into internal forces. So when we cut a beam at any point along its length, we can examine the internal forces. So when we cut a beam, there's always going to be M and V. M is the moment, N is the normal force, axial force is like the force acting in the X direction of the beam, and then shear force, which is acting straight down Y direction of the beam. So here we can see a diagram visualizing it. So shear force, yeah, that's shear force, axial force, and then moment. So axial force, positive is going to be in tension and negative is going to be in compression. That's the sign convention for axial force. And shear force, positive shear force result in a clockwise rotation of the cut section, and negative results in the anti-clockwise direction of the cut section. So bending moment, the positive bending moment causes the cut section to concave up, and negative causes to concave down. But if we want to find the value for M and V at any point along the beam, we can use shear force diagram, and bending moment diagram, SFD and BMD. So yeah, let's go to that, SFD. So here we have a beam, right? We got here a roller support, a pin support, and a roller support here. So we got AX, AY, and then BY there. First step of any beam question is to solve the reaction forces. Like I said, Fx equals 0, Fy equals 0, and sum of Ma equals 0. So sum of Fx equals 0, so we know that Ax equals 0 from just inspection. And now we move into a sum of Fy equals 0. So here Ay, and then we solve the UDL here. So just the area 4 meters by 3 kilonewtons per meters, that's 12 kilonewtons acting directly in the center of the UDL. So that's going to be 2 meters each way. 2 meters each way. And then, yeah, so now we can solve the some moment. So got 18 kilonewtons here acting downwards, so causing a clockwise direction, clockwise movement, so that's going to be negative. So negative 18 times 2, 12 kilonewtons acting down, so again causing clockwise, so negative 12 times 4, plus By anti-clockwise, so we adding it, By times 6, and here is going to be causing a clockwise rotation, so negative 6 times 8. So we're simplifying to 6By equals 132 and By equals 22 kilonewtons. Therefore, Ay equals 14 kilonewtons, By equals 22 kilonewtons. So with SFD and BMD, your diagram always has to end at 0. So enter 0 here, enter 0 here. So if your SFD and BMD doesn't end at 0, you got something wrong in the question. So yeah. So here we found that Ay equals to 14 kilonewtons, right? So we move up to 14 kilonewtons, and then you move across here. Wait, I just turn this sideways, maybe better. And then you move across here, and then you move 18 kilonewtons down. So you got this value is negative 4 kilonewtons. And you know how there's the UDL here, right? Between 2 meters and 6 meters, you have to draw a triangle down like that because there's a UDL there. So the value of that is 12 kilonewtons, so you move down to negative 16 kilonewtons triangulate. And then you got a force of By there acting up of 22 kilonewtons, so 6 kilonewtons up here. You move across there, and you got 6 kilonewtons down there, and you return to the x point, horizontal axis. So return to the original point, so the thing's right. So now we move on to BMD. So basically the BMD is just the area of the SFD. Oh shit. But basically the area of the SFD. So you got 2 meters there by 14 kilonewtons, so that's going to be 28. So you move up 28, so that's positive because it's above the x-axis, 28 there. And then you got the area of this section. We're going to calculate the rectangle and the triangle itself. So that's the area of that is 40. So that's below the horizontal axis, so you've got to move down 40 value to negative 12 here. Negative 12, and then the third area here is 6 kilonewtons by 2 meters, that's 12 kilonewton meters, so you move up to the original point, so the BMD and SFD checks out. Any questions so far for the shear force and bending moment? No, okay. Let's move on. And truss analysis. What's the purpose of truss analysis? So this is a truss bridge here. We can find the internal force of every single member truss using truss analysis, basically. Yeah. There are two methods of truss analysis. One is method of joints. This method involves analyzing each joint or node of truss separately, then using equilibrium to solve each joint at that node. So here's a simple example. So all members are 1 meter long and all angles are 60 degrees. And you've got a force here of 200 newtons. 200 newtons here, and then you've got a pin and a roller there. So you've got AX, AY, and EY. So every single question first, you've got to find the external forces, AX, AY, and EY. So sum of Fx equals 0, so Ax equals 0. Just observation. Ax here, you got no horizontal force at all in the truss, so Ax would just be equal 0, and then sum of Fy equals 0, so Ay plus Ey equals minus 200 equals 0, so it would be Ay plus Ey equals 200. And now we do sum of moments around A equals 0, so that's here 200 is acting down, pushing the whole truss down, so that's causing clockwise movement. So that would be negative 200 times 3. Where we get the 3 from? So negative 200 times 1.5. My bad. Sorry. Because this distance here is 1.5. That's 1, and then here.
Shouldn't be down here.
Wait, yeah. Just sorry. This is 0. Wait, sorry.
So this is one, right? This one.
Let's go to the base.
This one, and then down here.
Yeah. Sorry, my bad. Yeah, 1.5 meters. Yeah. And then EY is causing it to move in anti-clockwise direction. So plus EY times 2. So EY equals to 300 on 2 equal 150 newtons. So we solve AY and EY and AX. So now we need to choose the starting point or start analysis point wisely. So we always start from the point here. I start from node A because you found the reaction there already, so you only got two beams to figure out. So we draw a free body diagram at node A. So you got 50 newtons going up, and you got AC and AB there. So sum of Fy equals 0. So 50 plus AB sine 60, because imagine here, right, this is a vector and you're trying to add it up there. So this is AX and this is AY. So they're both moving in positive direction. So in the Y is going to be sine, and in the X is going to be cos. Yep, understood. So yeah, so sum of Fy equals 0. So we got 50 newtons here, plus by the AB sine 60 there. Plus AB sine 60 equals 0. So AB we found is to be negative 57.74 Newton. Or otherwise you say this AB equals to 57.74 Newtons acting compression. So what's the difference between compression and tension? So compression, so the force points towards the joint, and tension, it points away from the joint. So yeah, so now we do sum of Fx equals 0 to find the value of AC. So sum of Fx, we got the AC, the member AC there, that's acting in the X direction, and member AB here, the horizontal part of member AB there, acting in the X direction. So AC plus AB cos 60 equals 0, so AC equals to negative AB cos 60. We already found AB from up here. We sub that down there to find AC equals to 28.87 newtons in tension. So now let's analyze at point E, because we already figured out the external force there, and we can find members ED and EC. So here we sum of Fy equals 0, so we got 150 newtons there, plus the vertical section of member ED. So again, this member, the X vector is moving in the negative direction, and the Y is moving in the positive direction, the summation of the vectors. So that would result in a positive ED sine 60. So here we solve ED equals to negative 173.2 newtons, or 173.2 newtons in compression. So now we solve for Fx. So EC here is pointing this way. So negative EC minus ED cos 60. Oh, by the way, in every method of joint, just assume the members are acting in tension, so points away from the joint. Because if we get negative, we just redo the diagram again. So sum of Fx equals 0, so negative EC minus the X component of the member ED, so negative ED cos 60. So here we got EC equal negative ED cos 60. We already found ED there. We subbed it in there. So EC equals 86.6 newtons in tension. So pointing away from the joint. And now let's do an analysis from point B. So point B is there, so you got BA, BC, and BD.
You can slow down a little because we got time as well.
Alright, sweet. Yeah. We now answer from point B. So BA we already found as 57 point. So note that we found AB already, and AB equal BA equals to 57.74 newtons compression. So like I said, for compression members, it points towards the joint, and with tension it points away from the joint. So we can draw the diagram as 57.74 newtons pointing towards the node B. So again, we just do sum of Fy, sum of Fx equals 0. So start with sum of Fy equals 0 first. So here we got the vectors addition. So that's the x direction is moving in the positive direction, and both the x and y are moving in the positive direction. So yeah. So 57.74 sine 60 degrees. So we got the negative, here we got horizontal direction as well. Vertical, my bad. Got vertical here going down. And then minus BC sine 60 degrees equals 0. So we arrange all that. BC equals 57.74 newtons in tension. So so now we do sum Fx equals 0. So the horizontal aspect there, 57.74 cos 60 degrees, plus BD there, and then plus the horizontal vector of BC. So plus BC cos 60 degrees, which already found up there, into there, is so equals 0. So we found that BD equals negative 57.74 newtons, or 57.74 newtons in compression. So now we've found all this member, that's already been found, that's already been found, that's already been found, that's already been found, and that's already been found, that's already been found. So now we just got to take point from point D to find the last member, which is DC. So last analysis to find D. So we take it from point D there, so we draw FBD again, DB, DC, and we found ED as 173.2 newtons in compression, so it points towards the joint, and BD as 57.74 newtons in compression, so it points towards the joint. So now sum of Fx equals 0, so you got 57.74 there in positive, minus the DC there, minus DC cos 60 there, and then minus the I'll explain this here. Okay, so sum of Fx, you got negative 57.74 going there, and you got the DC cos 60 minus DC cos 60 there, and then minus 173.2 cos 60 there. So we got DC equal negative 57.72 newtons. So 57.72 newtons in compression. So now we have found every single member, every magnitude of the member in this truss, and the tension and compression. That's what they're going to ask you in the quiz in the final. So find all of the member magnitude and the direction. So direction is just compression or tension. And the second kind is method of section. So how do you know when to use method of section or method of joint? So if the question asks you to find every single members, so that's when you use method of joints. But if they only ask you to find one single member or one single section in this big truss, that's when you use method of section. So because it simplifies the equation much more, because they ask you in this particular question to find the member EG there. If you do method of joints, it would take you forever to figure out the member EG. So that's not you can't do that. So yeah. So for method of section, we make a specialized cut. So we're trying to find member EG. So we just cut it around this, make that cut there, and then we redraw the diagram like that.
Before you move on, there's some steps that I wrote up to for solving method of joints questions, right? So obviously, if our, let's say, truss looks something like this, these are pretty simple small truss. Give me a sec. Okay, so A, B, C, D, E. So first step, choose a point, right? They might, in the question, they might ask you, oh yeah, find the forces acting on point A, point B, right? Then you specifically choose either point A or point B. But after you choose a point, if they ask you to find all the forces in each of the members, then you would have to do it for each point individually, right? So you choose a point, draw a force body diagram for that point. This includes the forces acting in the beam, so in each of, not the beam, sorry, in the members. So in each of the members, like member DE, CE. So I'll do an example for A. So let's say there's a force acting down here, F1. I'll say here F2. Okay. You know what? I'll also do F3. So I'll choose point B. So point B. We can see there's a force 1 or F1 acting downwards first of all. This is an external force, F1. Now we also have the member BD, BA, and also the BC that's connected to that point B. Okay, so we're going to draw those three members in tension. So for example, we got BA acting this way, BC acting this way, and BD acting this way. When I mean by tension, I mean just pointing outwards. Okay, so you can either be in compression or tension. Tension is pretty much pulling outwards, so you're pretty much stretching it out. Okay, compression is the opposite, which means you'll be pushing it inwards. So you're pretty much compressing the beam. Okay. In general, we usually draw it as tension because tension is the positive sign convention. Okay. After you draw, let's say this is FBA, FBC, FBD. Right? After that, you can break each of the forces down into its respective x and y components. Okay? So there will be an angle that they'll give you. Let's say these are the same angles for simplicity. First of all, FBD only acts in the x direction. Okay, there's no y component to it at all. So I'll say the y component is equal to 0. FBD of x is equal to another positive sign convention is that y and x will be pointing to the right if it's positive, and y will be pointing upwards if it's positive. Okay, so we've got FBD acting in the positive direction towards the right. So we'll have FBDX being positive, FBD, and then you do that for each one of the FBA, FBC, F1 as well. And then you'd finally use your equilibrium equations. So you use sum of Fx equals 0, sum of Fy equals to 0, and also sum of the moments equals 0. Okay?
Oh, that's in methods section.
Oh, that's in methods section. So I'll say methods of section, MOS. That's in method of section, sorry. So in method of joints, you don't really need this, but main thing you need is sum of Fy equals to 0 and sum of Fx equals to 0. And then you can you would probably get some simultaneous equations, right? So
yeah.
you probably get some, let's say F1 minus FBA pointing downwards. What is that? Cos theta minus FBC cos theta. Sin theta?
Yeah, sin theta is going down.
That's sin theta.
Oh yeah.
Yeah, that's sin theta. It's cos theta pointing downwards,
Yeah.
right? And then also, and this is equal to 0. So we don't know each of the FBA, FBC. So you would have F1 in terms of FBA and FBC, okay? You'll do this for each one of the points, and you get equations that cancel out, and then you'll be able to find your respective forces in the members. So you know, member DE, DC, BC, and whatever, so on. Right? That's pretty much a little thing that I wanted to add. You can keep going with methods.
Oh yeah, method section. So yeah, we now we redraw the diagram. So yeah, again, we got a pin support there and roller support we found. So we just find the external force from sum of Fx equals 0, sum of Fy equals 0, and sum of moments equals 0. So we got 2.2 kilonewtons going up for that joint there. So now we take Fx, sum of Fy, and some moment at some point. So sum of Fx equals 0, so we got EG plus FH plus FG cos 60 equals 0, because that's the horizontal component of FG there. And we rearrange that to find EG equal minus FG cos 60 degrees minus FH. So now we find sum of Fy equals 0 to find the member FH, basically. Oh, no, don't, oh, sorry. Sum of Fy equals 0 to find the member FG. So we got minus 2 kilonewtons, minus 2 kilonewtons there, plus 2.2 kilonewtons going up, minus Fg sine 60 degrees equals to 0. So we found that Fg equals to 0.231 kilonewtons. Kilonewtons is just newtons times by 1,000, by the way. And now we apply moments equation to find Fh. So we take a moment around point A. So here we got negative 2 kilonewtons causing a clockwise direction. So that's going to be negative. Where is it? Sorry. So in this question, I'll start from Fh. So Fh is a horizontal force, but imagine your pulling is that way, so it's causing clockwise direction going down like that. So that would be negative Fh times the perpendicular distance, which is given here, 0.866. So yep, minus Fh times 0.886, and then Fg here we're taking moment from that, so both the vertical and horizontal. So horizontal component are positive and vertical is negative. So horizontal component is Fg cos 60 times by 0.86, and the vertical component minus Fg sine 60 times by 2.5. That's the distance from there to there. From there to there, perpendicular distance. So we figured out that Fh equal to negative 3 kilonewtons, or 3 kilonewtons compression. So now we're going to find Eg. Eg equals to minus Fg cos 60 minus Fh. We already found Fh and Fg, so we just sub it in. Eg equals to 2.885 kilonewtons in tension. So that's the question basically. So what take from truss analysis is when to use method of section or when to use method of joint. So when method of section, they just ask you to find one singular member in a big truss like this. So that's when you use method of section. Or when they ask you to find every single member in the truss, that's when you use method of joint. So that's basically what I've covered for statics. And Farhan's going to cover dynamics now, which is the harder part of the course. So, yeah. Want to start dynamics?
Oh, should we give them a break?
Oh yeah, and enjoy your break, just like the snaps at the front and stuff like that.
In the meantime, I'll get my stuff ready.
Well, very good.
You can just you know what? To be honest. Trust analysis. It's been. I don't know. one he showed you trust.
That's magical.
Oh, one step like
Let me just double check it's still on, because it turns itself off. It is on.
That's good.
I think we need the like white book cleaners.
I don't know, I just got asked. I'm pretty sure if I'm ready to
Yeah, the shit, but I think from experience, I like the other markers better.
I'll probably just do black.
Yeah, upper hips. I wrapped those. They're free from the teaching office and this.
Oh, is it?
Yeah.
So that you've done that.
Such a nice room.
We've done all this demonstration.
The static stuff.
Actually, it's
Yeah, but I'm not asked. Yeah, she's like,
Oh, let's get lunch.
Oh, bro,
I like the last one. Like,
I saw the first.
why do you get a label?
I saw the first like thing.
Alright,
I mean,
It's good to send over again.
thanks a lot.
Yeah. Oh,
Yeah,
see,
I'll be at this one.
I'm not.
And that sends one that is doing the transport.
Oh, yeah.
it's like easy for us. They can make it really.
That's my last one.
This is your last term?
Oh, no way.
Fuck, no way, dude.
It's a leave this thing. I'm sure you know.
Oh shit.
You
Yeah,
guys-
everything's recorded, isn't it?
No, I don't
I'm
do
not the
it.
same.
I'm trying to do it online.
Most people just take sheets for geotech.
Yeah, I
They
just feel like
watch
it's
the
kind of
recording.
No. I was there in person the whole time for episode 1. You actually passed me. Like, if you thought like
Just like a pretty
1300, I'll be there in person every single stage.
Yeah, but when you do geotech, no,
the thing you do at the
Yeah.
But
I
like
reckon
force,
it's
there's a
cool.
force
Oh.
in the next direction.
2002.
you've done, yeah. Oh, when you're doing the most of the course.
The actual
Right now?
Yeah.
when the force is acting.
This degree is not.
Yeah. So not compared like mechanical.
Yeah, those ones are big.
Yeah.
Just do a free body diagram and
It's
then
like
They just do it.
like
Friday, Tuesday, and Friday. Tuesday, Thursday.
Yeah.
Friday I have no class. I just can't do football.
Oh, Tuesday. Most people are not Fridays, actually.
have you done the
Yeah, this is because the
quiz yet?
Yeah.
Have you been? Tell me I was wrong.
Is there a lot of quick course Yeah.
I did it.
Like they give you like.
I did it once.
I find it
The
difficult.
second question I was doing, like, not sure, so I did it again.
Yeah. I think yeah. I think I've just like
Yeah. It's not important for like anything like
Oh, actually, I'm kind of regretting, like, now it's happens to be relevant for my thesis.
that. Is it?
But, like, it wouldn't be for most people's thesis. It's just kind of involves probability.
Oh, what?
Yeah, so, but, like, oh, and we use the numerics as well.
Oh, shit.
But, like, it's all like I'm relearning it anyway. It's not like,
So what's your thesis? Didn't go well.
it's about, like, probability to the bed.
Oh,
Like,
okay.
it's just simulating and, like, digital testing. Which is
Yeah.
yeah,
instead of
I believe it works really.
it's just like
Yes, bro. Does it get rich like most of you need this to be a bit of
Think of
whatever.
a budget, I swear.
Sorry, what? I think Eric left.
I thought that. That's
Oh, we're sorry.
And then I was like, I guess.
Alright, guys, grab your attention. We'll
Alright.
just continue now with the dynamics half.
Wait, give me a sec. So there were some people who walked in late. The stuff I wanted to recover was mainly this beam stuff over here. So like SFD, BMD, AFD. SFD, I put on the board here. Oh, it's gone now. SFD just means shear force diagram, which he also went through bending moment diagram, but he didn't go through axial force diagram. It's not that relevant, is it? It's not that relevant. You might see it here and there, but you're not going to be doing many questions on it. Okay. What I'm going to be going through is introduction to dynamics and kinematics of particles and the kinetics of particles. Okay. I'll also be going through work in energy, impulse, and momentum only for particles. So if I scroll down a little, dynamics can be broken up into kinematics or kinetics. Kinematics pretty much just describes the motion of an object. Alright? Kinetics, however, is concerned with the forces acting on an object and the motion of the object as well. Okay? So it's a combination of kinematics and some extra forces. Okay? So kinematics, we can break it up, both kinematics and kinetics, we can break it up into either particle or rigid bodies. Okay? What I won't be going through a bunch of rigid bodies. I'll be going through particle kinematics, particle kinetics, and a bit of mass moment of inertia from rigid bodies. Okay? I think people are copying it down. You guys like a few minutes to copy it down. And some of the 2D coordinate systems I just copied from your Bible. From the Bible. Yeah. I already showed you some of this stuff. I'll just go through it in a bit. Yeah. I'll go through in a bit more detail. Because like when I did it with the mechanical stream, they didn't have much on it. They were like, oh yeah, this is the NT coordinate system, this is the XY coordinate system.
Yeah.
They didn't go through in depth as much as the Bible, so I just stole them. Okay. They didn't even go through like any of the inertia stuff. They like assumed like. Okay. So dynamics is concerned with the motion of objects, i.e. when the sum of forces does not equal to 0. We'll mainly be looking at sum of forces is equal to MA, which is Newton's second law. Okay. I'll go into more in depth in kinetics. It's more related to kinetics. Okay. Before I go through coordinate systems, I want to go through vector linear motion. So this is the first part of particle kinematics, which we got up here. Here it is. Okay. So rectilinear motion is the motion along a straight line. So pretty much talking about 1D motion. So let's say there's a particle and it's moving along a straight line with velocity v, and it's somewhat covering some displacement s. Okay. So rectilinear motion have 3 different quantities that we have to worry about: position, given by s, or displacement, velocity, and acceleration. Each one of these, position, velocity, and acceleration, are functions of time. So we can say this one over here, s of t, v of t, and a of t. So firstly, I'll go through velocity. There's 2 different types of velocities. There's average velocity and instantaneous velocities. You guys might have seen this in Phys 1A. But average velocity, if I draw up a graph for it, so let's say ST and then we have a graph that looks somewhat like this. Okay. Let's take two different time points. So t1 and t2. In this case, where t2 is greater than t1. Okay. The average velocity is just a gradient between these 2 points. So I'll draw up a gradient this way. I'll do a different color. This over here. So this point over here, we can treat it as t2 s2. The point s2, and this one down here will be s1. Okay. Point down here will be t1 s1. Yep. And using our gradient formula that we learned all the way in like year 9 and year 10, m is equal to rise over run, or also known, also more commonly, y2 minus y1 over x2 minus x1. And from this formula, we pretty much get the average velocity being the change in displacement over the change in time. Okay. So I'll rub this out. Change in displacement, we can say s2 minus s1 over t2 minus t1, where s2 is our final displacement, s1 is our initial displacement, t2 is our final time, t1 is our initial time. Okay. Okay, all good? Can I move on? Okay. So now I'm going to move on to instantaneous velocity. This is a bit more specific than average velocity. It takes it uses calculus to calculate the velocity. Okay. So the formula that we know for instantaneous velocity is that v is equal to ds on dt or s dot. Okay. By the way, in mechanics of physics, s the dot represents derivative with respect to time. Okay. S dash is usually derivative with respect to x, and s dot is with respect to time. Okay, so I'll say with respect to time. Okay. And again in Math 1A or Phys 1A, you guys might have learned that you can separate this differential equation. Okay, we're going to separate it, and we're going to take the dt to the side of the to the left side, which is the v. Okay, and when we integrate both sides, we get a new equation. We get the integral of, with respect to displacement, is equal to the integral of velocity with respect to time. Okay, over here. So setting up another graph over here, which I've done from before, we have a velocity function v of t and two time points over here, time 1 and time 2. Okay. The area under the curve between these 2 points will give us the change in displacement. Okay, so displacement, I'll just say the integral from s1 to s2 of ds. All good? Okay. What I'll do, I'll go through a quick example using the separable ordinary differential equations method. So we have velocity is equal to 3t minus 2t cubed. All right, actually what I'll do, I'll go through this on the board. So we have velocity, is it 3t minus 2t cubed? So I've already shown you guys the answer, but does anyone know how we can break up that v into some sort of differential? Sorry? ds over dt, exactly. So I'm going to say ds over dt is equal to 3t minus 2t cubed. 2t cubed. And we can bring the dt over to this side and break it down into ds will equal to 3t minus 2t cubed dt. Okay? Now, we can integrate both sides, from T1 to T2, and at T1 the displacement will be S1, at T2 the displacement will be S2. So pretty much what we get is that, I'll bring it over here, not much space. The integral of ds between S2 and S1 will give us, we're just going to have to integrate the 3t minus 2t cubed, okay? We get, what is it, 3 over 2t squared minus 1 over 2t to the power 4 between t1 and t2. Right? So this is called the separable ODE method. Okay. Which I've pretty much got over here. Then there's also an initial value slash initial conditions method, also known as IVPs. This is when they give us initially time, when time is equal to 0, displacement might equal to something else. Okay. I've got a question later on that I'll go through, I think. Let me check. Yeah, over here. This one's the IVP. Okay, so far we've covered all of velocity. Any questions? No? Okay. I'll move on to acceleration. Average acceleration is the same business, except our graph will look something like this. Instead of s being on the y-axis, it will be v, and x-axis will always be time. Okay. This will be our vt. Take these 2 points. Find the gradient. So this gradient m will equal to average acceleration. Say vf minus vi. So final velocity minus initial velocity divided by final time minus initial time. Okay. And then just like velocity, we've also got instantaneous acceleration. Okay. Where acceleration is equal to dv on dt, v dot, or s double dot. Okay, so which is just a secondary derivative with respect to time. Okay. Okay. And again, we can break it up. We can say that the integral of the dv between v1 and v2 is equal to the acceleration between integral of acceleration with respect to time from t1 to t2. Okay. So drawing up an acceleration time graph, AT graph, so this is a AT graph. Yep. So the area under the curve between t1 and t2 gives us our velocity. Give you guys like a minute to copy it down. Is it blurry, by the way?
No, that's good.
Okay, okay. I think it might be a bit blurry in the recording.
Is it Discord?
Yeah. We'll have to check afterwards.
You can certainly with these like motion straight.
Oh, is it? Like this?
It's fine now.
Okay, that's good. Okay. Okay. One more thing I'm going to cover in, two more things I'm going to cover in rectilinear motion. Sometimes we're going to have to eliminate the variable t. Okay, so we're going to have to somehow relate acceleration and velocity, or acceleration and displacement, without taking account into time. Okay, so we know that dt is equal to ds over dv, which is also equal to dv over a. Okay. Since they're equal to each other, we can just say that v dv is equal to a ds. Integrating both sides with respect to, on the left side it will be dv, on the right side we're taking acceleration with respect to ds. So acceleration with respect to displacement. Okay. what that gives us is that, I'll break this down a bit further. I'll say that v2 squared over 2 minus v1 squared over 2 is equal to the integral from S1 to S2 of a ds. So, in the off chance that you ever get a weird graph and AS graph, so this is a acceleration displacement graph. Yeah. The area under the graph will always be the change in the velocity squared divided by 2. It's a bit confusing to think about because we've always thought about the area being either velocity or displacement. But in this case, you're going to have to think about it as this. I don't think there's an exact term to what that's called, but we're just going to have to work with it. Okay? Yeah, this is a bit more weird compared to the other two that we just looked at. Okay. So the main type of graphs that you guys do get are going to be acceleration time graph, velocity time graph, displacement time graphs, and maybe acceleration displacement graphs. Those are the 4 types of graphs you guys might get. Okay. Jared, you listening? Alright, shut up. Hey, constant acceleration equation. So these are called the Suvat formulas, and you guys probably did this from Phys 1A or higher Phys 1A. Yeah. So velocity is equal to initial velocity. So these are initial velocity. Initial velocity. Acceleration, and this is our change in time. Change in time. So imagine, I'll put this one up. Imagine a particle is moving in a straight, because again, we're moving in straight lines, okay? 1D motion, rectilinear motion. It has a velocity v0 and it's accelerating. So I'll say constant acceleration of acceleration of A. So let's say this is T initial, T final. The velocity at this point, so velocity is equal to what? Velocity at this point would be our initial velocity plus the acceleration multiplied by the change in time, which would be TF minus T0. In this case, I just did T minus T0. Okay. So you can also do T minus T0. So that's velocity. This one's going to be for displacement, okay? So we have an initial displacement from the origin with respect to the origin, plus our v0 from before, multiplied by change in time. So I'll say change in time. Can you guys see the green? Okay, good. Plus a half a times the change in time squared. So change in time or squared. Okay. If you guys noticed, the S equation that we have here is just the V equation, but integrated with respect to time. So I'll just say that to get from here to here, you're gonna have to integrate with respect to time. Okay? And this final equation is V squared minus V0 squared plus 2A change in S. So this is change in S. I don't know where this equation actually comes from, but
It comes from the base
Oh, you talking about this one over here?
Yeah, the exact same, but it's constant acceleration versus change.
Oh, okay. I didn't know that. Oh, so if it's a constant acceleration.
If you change the other one, and then
Oh, okay. So I
you
see.
go
I
back
see.
to constant acceleration.
So since it's constant, you can take it back like that. You say leave it to a s2 minus s1. Right?
Yeah.
Okay.
So v squared final minus v squared initial on 2, and then you can multiply by 2.
Yeah.
So v squared minus u squared is 2as, and then you can add it.
Oh, okay.
V squared is u squared. plus
Yeah, so I'll just put down what he just said. So we have v2 squared over 2 minus v1 squared over 2 is equal to, from s1 to s2, a ds. Right? Now, if our acceleration is constant, right? So if you've ever integrated a constant before, so 2dx, we know this is just equal to 2x, right? So we can just treat this as a s from the bounds of s1 and s2, which gives us a s2 minus s1. And we know that in this over here, we get v2 squared minus v1 squared is equal to 2a s2 minus s1. v2 squared is equal to v1 squared minus plus 2a s2 minus s1. Oh, so that's where it comes from. Okay. Oh, sick. Okay. Okay. Yeah, so that's the last equation over there. Alright, once you guys are fine with that, are you guys all good with that? Bradley? All good? Okay. I'll start going through projectile motion. Projectile motion is like a very small part of engine mechanics. They don't really ask it that much. But in the off chance you do get the question, you guys will be prepared, okay? So, first of all, when it comes to projectile motion, the path will always follow a parabolic path. So it will always be parabolic. So we don't take a look at resisted motion in mechanics. If you guys did 4U math in high school, you guys might have seen resisted motion. And your motion goes something like that. Right? But we don't really give a shit about that, okay? We're always going to say that it's always parabola. It's always a parabola. Okay? Apart from that, the other most important thing that you guys are going to have to remember, the horizontal acceleration, AX, is always going to be 0, and the vertical acceleration is always going to be negative 9.8 meters per second, which is just gravity. Okay. I'm going to ask you guys a question. Since horizontal acceleration is always 0, how does it affect the horizontal velocity as the path goes?
It's just constant.
So yeah, exactly. So this will just mean velocity in is constant. Alright. We go up to the formula that we had over here. If we sub in a is equal to 0, so ax is equal to 0, the velocity we will always get, no matter at what time point we are, will always be v0. Okay? Okay. So in projectile motion, we have an initial velocity v0, which we can break down into vx0 and vy0. Okay? This is the initial velocity in the x direction, vx0, and in the y direction, we have vy0 being our initial velocity. All right. So I'll drop a quick triangle. This will be vx0, vy0. And the angle, in this case, will be theta. it is a parabolic path, so it should technically look something like this. But we still say, since it's such a small angle, small difference, I mean, we'll just say theta, the angle is theta over here. Even though it's not really a straight line. It's like a bit curved. Shit. It's a bit curved, but we don't really care. Okay? One more thing to note, at the peak height, the velocity will be 0. Okay? The reason for that, I'll go through just in a sec. Okay? I've got a table here I want you guys to copy down. So I've got in the x direction and in the y direction, and different quantities. So I've got initial velocity, velocity at any time point, t, and displacement at any time point. Okay? Yeah. Oh, projectile. Oh, so apparently this is very frequently asked. Is it?
Yeah.
Did you get it?
Yeah.
Shit. Okay.
Finals and the quiz too.
And the quiz too.
Yeah.
Damn. Okay. Because like when I did it, it was a bit different.
Yeah, like you can understand.
Okay. Yeah. Okay. So you guys are all doing engine mechanics in term 2. Is this term? You guys will probably see this a lot. Okay. I take back what I said before. So initial velocity from the triangle that I drew up here, we can break it down into cos theta and sine theta. So in the x direction, we have v0 cos theta. In the y direction, v0 sine theta. So in x direction, holy shit. I'm going to say velocity. Velocity at, I said VT. So velocity at any point is equal to Vx0, which is V0 cos theta. But in the y direction, plus AT, right? So I gotta fix something up in my notes. Down here should be AY. Okay. Plus AYT, which is V0 sine theta minus 9.81 times T. Gravity we always take as 9.81, unless in the question they say use 9.8 or 9.79. Okay. And as I said before, we can go from velocity to displacement by integrating with respect to t. Okay? So since this term equals to 0, and this Vx0 is always constant, right? Our displacement, x displacement, is always Vx0t, which is equal to, as I put on the board, V0 cos theta t. Okay. And our sy, it's very similar to this, except when you're integrating, you're going to integrate between the bounds sy and sy0. So an initial displacement in the y direction. Sometimes you might get a projectile motion question like this. Like that. Okay. So where this over here is our sy0. And in the case that I put up here, our sy0 is equal to 0. Okay? Where we take this as the origin point. Okay? Okay. Does this make sense to everyone? Yeah. Okay, I'm probably gonna add one more thing because, as Quang said, they go over it a lot. I'll probably show you guys the derivation to the maximum height formula. So, of okay, so first of all, we know that at max height, Vy is equal to 0. Oh, I can explain why that's the case, okay? So taking a look over here. Oh wait, they can't see that. I'll do it on the iPad. Okay. So as we discussed before, the velocity, the x velocity never changes. It will always be constant. So I'll just draw at any point, this x velocity will be constant. So when I move my constant, just look at the size of the line. Yeah, it will always be the same at any point. Oh shit, that's a bit long. And it will always be pointing in the same direction. Okay. So I'll say red is our x velocity, and I'll say blue will be our y velocity. Okay. So it has an initial velocity of Vy 0, but as we move further to the right, the velocity of y will slowly start to decrease because of the deceleration of gravity, right? So it will be something like, it will be a bit smaller, get a bit smaller, even more, and at this point it will just be 0, right? So I'll say Vy is equal to 0. So, but on the way down, it will start to increase again, right? Because our velocity is going the same direction as gravity. So, a bit bigger, larger, and the largest. Okay, that's Vy. Okay. That's pretty much what the velocity distribution will look like along the path. Okay. Okay. So for the derivation, at max height, we know that Vy is equal to 0. And what's the formula for Vy again? Someone?
Initial, you could go initial velocity sine theta.
Yep. Sine theta?
Yep. Minus 9.81 times t.
Minus 9.81 times. Perfect. Okay. And if this equals to 0, we can say that V0 sine theta is equal to 9.81 times t. 9.81 times t. Okay, what I'm going to do from here is that I'm going to make t the subject. So V0 sine theta over 9.81. So as it moves along, as time goes on, at this time point, so in this, at this point, the time will equal to V0 sine theta all over 9.81. Okay. And we know that the y displacement formula is given by, in this case, I'm not going to take S0 because our origin is at 0. I'm going to say, what is it? V0 sine theta t minus 9.81 over 2 t squared. Is that right? Yes. Okay. Okay. what I'm going to do, I'm going to say sub in our t value over here. This will give us v0 sine theta multiplied by v0 sine theta all over 9.81 minus 9.81 over 2 times v0 sine theta all over 9.81 all squared. Simplifying this, we get v0 sine theta, v0 squared sine squared of theta all over 9.81 minus, there's a 9.81 that cancels from here and here, so we'll get v0 squared sine squared of theta all over 2 times 9.81. Simplifying this down even further, we can say that sy, I'll just say h max, so maximum height will equal to v0 squared sine squared of theta all over 2g, or 2 times 9.81. Okay. This is the maximum height formula. Wait, Henry, is it true that during term 2 you guys get like a lot of projectile motion questions?
For the midterm?
Midterm, finals, whatever. Because when I did it with Kellerman, there was like not a single question of projectile motion. That
It wasn't a single.
there was like one, like some of the homeworks, and that's it.
I think before they had a lot of projectile motion, and then I told my kids to like study it a lot, and then there was a lot of curvilinear motion.
Curvilinear
instead.
motion.
Fucking we
That's so true.
So I don't know. It's really hard to say.
Okay,
Yeah.
no worries. Okay, that's fine. I still went through like most of the key stuff for projectile motion. Okay, everyone got that copy down? Yeah. Okay. So I'll move on to relative motion now. So there's a key formula for relative motion. In relative motion, I usually like to work with vectors. It makes it a bit easier to understand. So we can say the velocity of A, oh shit. So this just says velocity of A relative to B. So velocity V of A relative to V of B, which is given by this formula, VA minus VB. Okay. And as you can see from the diagram that I've drawn here, it's pretty much just VB plus the velocity of A with respect to B. Relative to B. And similarly, there's also relative motion formulas for position and acceleration. But this is more used in rigid bodies, which you guys will see towards the later ends of the term. Okay. And there's also some important identities I put up here in the corner. I'll bring it back down actually. So the relative velocity of A to B is pretty much just the negative relative velocity of B to A. Okay. Okay. Once everyone's got that copied down, I'll move on to particle kinetics. So that's that covers pretty much all of particle kinematics. I'll move on to particle kinetics now. Particle kinetics. What do we cover in particle kinetics? How to apply Newton's second law along with force body diagrams. How can we model forces from springs, strings, friction, and gravity in a dynamic setting? How can we work with impulse, energy, work, and momentum in a dynamic setting again? And how do we know when to apply each three of these? Okay. So a summary of work / energy. This is a formula you guys will be seeing quite a lot. The work between state 1 and 2 is equal to the integral of the force with respect to displacement, okay, between points A and points B. if displacement is linear, we get this formula over here. So can I move on? Yeah? Okay. So the next formula that you guys will see is pretty much a formula you guys will be seeing throughout all of not all of dynamics, most of dynamics, most of kinematics and kinetics, right? It's called the Big Mama formula, or the Holy Grail formula. Okay? So this is like a pretty OP formula which covers most of, pretty much all of work. So between states 1 and 2, you take into account kinetic energy, gravitational potential energy, and also energy from springs. Right? And what I've done over here, I've broken up some the most of the formulas that you guys will be seeing for kinetic energy, gravitational potential energy, and elastic energy. So this one you guys might have seen in Phys 1A. This one you guys also might have seen in Phys 1A as well. Okay. I've put up a work formula here as well, which includes the moments and radians, but this one we usually see in rigid bodies. Okay, you guys don't usually see in particle kinetics. Okay, so I'll say more for rigid bodies. Okay. You guys don't need to copy everything down word for word because I'll be uploading this stuff anyways, right? So I'll quickly go through a summary of impulse momentum, some basic formulas. A momentum formula, G is equal to M multiplied by V, which is also equal to momentum times derivative of acceleration with respect to time. Mass times derivative of acceleration with respect to time. Impulse given by J between states 1 and 2 is just a change in momentum. So this one over here is change in momentum. Which is also just force multiplied by the change in time, given by this momentum formula over here. Okay. So conservation of momentum and energy you guys will see as well, where it occurs when the impulse is equal to 0. So the sum of MF/VF, also known as mass final, velocity final, is equal to the sum of mass initial, velocity initial, over here. And when you have two particles colliding, so something like this, this is A, this is B, it's moving with velocity V, with velocity A. Okay. This has a mass A, mass B, and when they do collide, they have a force that act on each other. So this would be the force of A onto B, and this would be the force of B onto A. Okay. Where force of AB is equal to minus force of BA. Right. You guys also saw this stuff in Phys 1A. Okay. Okay. Coefficient of restitution. Does Weigel go through coefficient of restitution? Henry? Does Weigel go through coefficient of restitution?
Yes, he does.
He does? Okay. Okay. So while the linear momentum of a system is conserved before and after the impact, the kinetic energy isn't necessarily conserved. So there's a few different reasons that it might occur. Most common: friction, heat generation, sound radiation, and plastic deformation. Right? And this is the formula that governs elastic, what is it? Coefficient of restitution / elasticity. Okay? What it actually is that it gives us more information about the type of collision between two particles. If it's equal to 1, it's an elastic collision. If it's between 0 and 1, it's a plastic collision. If it's equal to 0, it's called a perfectly inelastic collision. And if I'm not wrong, isn't perfectly inelastic collision when they stick together and they move as one body? Okay. Next, I'm going to go through just a little bit of rigid bodies, mainly mass moment of inertia. So you guys also saw some of this stuff in Phys 1A. There's a lot of overlap between mechanics and Phys 1A. So consider a rigid body and the arbitrary axis P shown in the figure. I did not include the figure. Oh, no. Shit. Okay, it's fine. The mass moment of inertia about the axis P, or on any axis, arbitrary axis, is defined as inertia is equal to the integral of r squared dm, where we're integrating along the mass. This is mass moment of inertia. Mass moment of inertia. It will always be a positive quantity, and it has units kilograms meter squared. Okay. These are the two types of shapes you guys will see the most: a thin rectangular plate and a thin circular disc. Okay. Mainly, I think you guys will be working with IXX and yeah, pretty much just IXX. They might ask you IZZ or IYY as well, but mainly you guys are seeing these ones. I don't know if it's on the formula sheet for you guys, but for when I did it, I didn't have it on the formula sheet, so I had to know the derivation for it as well. Sorry? Oh, is it open book? Finals?
Yeah, it's right there.
Oh, it's open book for you guys. Okay, it wasn't open book for me. Okay. Okay. And the most important formula when it comes to mass moment of inertia is the parallel axis theorem, where the total moment of inertia is given by the mass moment of inertia about the body's center, so the body that we're analyzing. So in this case, I've got a body here, and the point G, which is just the center of the body. Okay. So we're going to be taking a look at the inertia just of the body with respect to its own center, and then we're going to be adding an md squared. All right. The md squared, what it does is shifts the moment of inertia from point G to point A. So like it shifts the what's it called? Sorry?
Center of mass.
Sort of. Yeah, you can think of it like that as well. I forgot the word. Centroid. Yeah, yeah. It's mass moment of inertia though. It's not second moment of area. I'm stuck in solids. Okay, I'll add into my notes when I remember, but this is the formula you guys will be mainly working with. Okay, this is just the perpendicular distance between the parallel axes. Okay. Okay. One more thing is the radius of gyration. So the mass moment of inertia of a body about a specific axis can be defined using the radius of gyration k. Okay? It is a measure of the distribution of the body's mass about the axis which the moment is defined. Right? So if it's defined about the arbitrary p-axis, this I will be, you'll be using this formula over here. Right? But if it's about the body's own center, you guys don't need to worry about the md squared. You guys would just need to worry about ig. Okay. And there's two formulas. I is equal to mk squared, or sometimes they tell you to find what k is. So you're going to be square rooting I over m. Okay. So I'll probably just go through one problem because we have 10 minutes left, or maybe this one as well. Okay. So this is the first thing that we looked at, rectilinear motion, right? So a sphere is fired downwards into a medium with an initial speed of 27 meters per second. If it experiences a deceleration of a equals to minus 6t, so we have acceleration in terms of t, meters per second squared, determine the distance traveled before it stops. Okay? So we're trying to find s when it stops, meaning when v equals to 0. So a few things we're going to point down. V0 is equal to 27 meters per second. A is equal to minus 6t. And that's all they've given us. V0 should be negative, by the way, because it's pointing the negative direction. Give me one sec. Okay, yep. Okay, so first of all, we know that acceleration is dv on dt, and we can rearrange, make dv the subject. Minus 6t dt. And again, we can integrate both sides. We've seen this plenty of times before. Okay. So we can say between the points t0 and t, v0 and v. Right? What is t0 and what is v0? Anyone know? What have they given us in the question? Sorry? You don't need it? Are you sure?
You could go T0 is just 0.
Yeah, t0 is just 0, and v0 being?
It has to be negative 27.
Negative 27, yeah. So this will just give us v plus 27 is equal to minus 3t squared divided by 2, yeah, minus 3t squared. So we have v, a velocity formula of minus 3t squared minus 27. That poses a problem because t squared becomes negative. We're just going to take, we can take v0 as positive. Let's work with that for now. Okay, and we're pretty much trying to find what the position when v is equal to 0. Okay, so before that we can find when it actually stops. So what the t value is when v is equal to 0. So let v equal to 0. Hold on. So let v is equal to 0, we get 3t squared is equal to 27. T is equal to 3 seconds. Right? Okay, there's one more thing we have to do. We have to integrate velocity with respect to time. So I'm going to say that ds on dt is equal to minus 3t squared plus 27. Integral of ds is equal to the integral of minus 3t squared plus 27 dt. Again, we know t0 is equal to 0. S0, we'll take it as 0 as well. We're integrating between 0 and s. So you get s is equal to minus t cubed plus 27t. All right. Okay. All we need to do is sub in t is equal to 3, and we get s is equal to, what would that be? Minus 3 cubed plus 27 times 3 gives us 54 meters. So it travels 54 meters before the particle eventually stops. Alright. I think
you've done the right thing, but we take the downwards direction.
yeah, we have to take downwards as positive, which is they've told us here.
Yeah.
right? So yeah,
If you want to take opposites the negative direction, you set the initial velocity to negative 27, but then you'd have to set the acceleration to be positive instead. It's the same thing.
oh yeah, that's true.
As long as they're in opposite directions.
Yeah. Okay. Yeah. Oh, okay, so this would become positive, right?
If you want to do it that way.
Yeah, okay. Now, but for simplicity, we're just going to say S is positive downwards.
Yeah.
I don't think I've got time for any other problems, so we'll just end it there for now, for today.
Alright, yeah, thanks to Farhan and Craig. They've done a great job, and yeah, it's like them volunteering their spare time, and of course they don't get paid or anything for this, so anyhow, let's give them a round of applause. Can we stop the recording?
Yeah, sure.
Yeah, just